Today we are going to discuss about the sets. So sets are defined as a well defined collection of objects. So what is well defined is, for example, if I say days in a week, right? So we can collect the days in a week like Monday to Sunday, right? So Monday, right, like that, till say Sunday, right? So this collection contains 7 names, right? Monday to Sunday. So this is a well defined because we know exactly what members are present in this and what members are not. For example, if I say June, right, some name, right, this is not in this collection, right? Only it contains Monday, Tuesday, Wednesday, Thursday, Friday, Saturday and Sunday, right? Only those names it contains, days in a week. Whereas June is a different name, it's altogether an unrelated name which is not in this. So we can clearly distinguish what are the members and what are not the members of this. So all the names apart from these Monday to Sunday, right, so they don't belong to this collection. So it's a well defined collection. Now if I say poets in India, right, poets, I would say good poets, right? Instead of just poets, I would say good poets in India. So if I say good poets, what is the meaning of good poets? It differs from person to person. That's why there is an ambiguity in what poet names get into this collection. Somebody might put some collection, right, which differs from other person, right? So there is no universal acceptance criteria as to what do we mean by good poets. So that's why this is not a well defined collection, hence it is not a set. Okay. Similarly, for example, if I say prime factors of 20, for example, right? So prime factors of 20, we can find the factors of 20 and then we can say among those factors the only prime factors we have is 2 and 5, right? Only these two are the prime factors of 20, right? This is how actually we can list out, and this is a well defined because we know that only two numbers are there, 2 and 5, and so it is easier, it is identified unambiguously, right? So that's why this collection is also a well defined one, and hence it is a set. So now we understood what do we mean by set. Now let's talk about how do we represent the set, right? So we usually represent the set and list them inside the open and curly brace, right? So this is how we represent. For example, prime factors of 20, I represent it inside the open and closed curly brace 2, 5. This is a usual way of representing the set. And one more notation we want to understand is small letters are usually used to denote an element. For example, if I say suppose A is an element in set capital A. So usually we represent the element or object inside a set as a small letter, and the set itself we represent it using capital letters, right, like A, B, C, capital A, B, C, and similarly here small a, small b, and small x, small y, like that. Okay, so this is how we actually denote the elements and the sets. And next comes how do we symbolically represent a membership. Suppose I mentioned that suppose A is an element of capital A, right, set capital A. So how do we represent that is A belongs to, this is what we say, A belongs to capital A. This is actually belongs to, right. This symbol is used, right, this symbol is used to denote the mentioning of belongs to, right. And if for example prime factors of 22 and 5 are the prime factors. Now if I say 3 is not belonging to, suppose if I call this set prime factors of 20 as B, for example, right, as a notation, if I say B, then I know that 3 does not belong to B, right, 3 does not belong to B. So this represents this when we use this symbol, right, epsilon and then one cross mark, then it means that does not belong, right, does not belong. And one more notation that we need to remember is, suppose if we list elements, for example I can say odd natural numbers, right. For example, if I say odd natural numbers, I will represent this as 1. I can list out these as I can say 1, 3, 5, and then dot dot dot. This dot dot dot, when we use the dot dot dot, it means that this pattern continues. 1, then 3, right, and then plus 2 5 comes, and plus 2 7 comes, like that. This pattern continues. So dot 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 means we say that the pattern continues indefinitely, right, pattern continues indefinitely, right. That is what we mean by the dot dot dot. So this is another notation we use to represent the to mention that the pattern continues indefinitely. It means you will have infinite number of elements in that. Okay, so next we will try to understand different forms of denoting this set, right. One is, we call it as a roster form, right. This we call it as a roster form. In the roster form, we represent the set as listing of all the elements inside curly braces, right. Say as we saw earlier, prime factors of 20. So we saw that as 2, 5, right. So inside the curly brace you list out all the elements. Okay, this is the roster form. And the next one is set builder form. Set builder form. In the set builder form, we provide recipe, right, recipe for the set, right. We actually provide the formula, or the condition, or the characteristic of that of each of the elements in that. So how do we do that is, for example, the prime factors of 20 how do we represent this as a set builder form is, I would say this is an element x which is a variable such that x is prime factor of 20, right? So this is the set builder form, and we can convert it to the roster form by figuring out what elements are there inside, inside this set, right? So this and this are actually convertible from one to another. They are in different form, that's all, right? The first one we put the we listed the elements inside the curly brace, so this is the final form, whereas the second one is basically a set builder form where we actually provide the receive or provide the condition or provide the formula or characteristic of each of the element, right? So another example is odd natural numbers, right? Odd natural numbers less than 10, right? Odd natural numbers less than 10. So how do we say is, first let us put that in set builder form. So in the set builder form, right, how do you represent that is, you take, say for example, this is an element A, where A is a element of the set such that A is, so this colon, right, it says such that, or it provides the condition, after colon whatever we write is the condition or characteristic or the property of the element, right? A is such that A is odd natural number less than 10, right? So this is the set builder form, right? This is the set builder form. Now how do we convert this to roster form is, now I can figure out by checking the property of this element, right? A is odd natural number less than 10 means I can list out that 1, right, 3, 5, 7, right, 9, right? So 11 is actually greater than 10, right? So I will not list that other elements, right? So 1, 3, 5, 7 and 9. So this is the roster form, the set. Okay. Next, two important things we need to understand about the sets is, the first thing is order does not matter. Order does not matter. Order does not matter. What does it mean is, say for example, if A and B are elements in a set, it is same as B comma A. In whatever order you collect the elements, right, the set does not change, right? So both these are actually equal. The second important property is repetition of elements. Repetition of elements do not alter the set. What does it mean is, say BA is there, right? So I can have, say, repeat the B 2 times and I can repeat A 3 times, or how many number of times I can repeat, still the set remains the same. In the shortest form, or in the, we can say in the simplest form, it remains the same. So if you want to reduce a given set to a simplest form is, just list all elements uniquely. List all the elements uniquely to get the simplest form of set. Simplest form of set. Alright, so this is another important property that we need to understand. So next we will look at some common notations we use to represent some of the well-defined sets, especially in the number systems, right? For example, we use capital letter N to represent set of natural numbers, right? Set of natural numbers, okay? And we use so we know that set of natural numbers, it starts with 1, 2, 3 and then dot dot dot. It means this pattern continues. And we use Z to represent set of integers, okay? Set of integers. So this set of integers, we know that it extends to the minus infinity, right? And then you have -1. So it actually dot 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 on the left side as well. Means it extends towards the left side, towards the negative infinity side, and then -1, 0, 1, 2, and then it extends on the right side, on the positive side, positive infinity, right? So this is how we represent the integers. And then we'll be having the rational numbers, right? So the set of rational numbers, it's called as set of rational numbers. Set of rational numbers, so we can write this in the set builder form as, right, because since this is a huge set, right, we actually can represent this rational number in the set builder form, where we know the characteristic of or the property of each element, right? So I can say it is of the form small p over q. It is a ratio of two integers, right? So I would say p over q, where, right, p and q are belonging to the integer set, right? And q is not equal to 0, right? So this is the set builder form of the rational numbers, right? Okay. And then we will have q dash to represent irrational numbers, right? Irrational numbers. Irrational numbers means that the numbers, right, which can't be written in the ratio form, written in p over q, right, which cannot be written in p over q are irrational numbers, right, are irrational numbers. So basically whichever the number are not rational numbers, right, they are actually irrational numbers, right? And then the set of real numbers, right, real numbers, it basically contains both rational number and irrational, both rational and irrational, both rational and irrational numbers, okay, both rational and irrational numbers. So these are the common notations, right, we use to represent these frequently used sets in mathematics. So we have one more called as W, right? This is a whole number set, set of whole numbers. So we have this natural number set, right? So if you add 0 to the natural number set, we will get the set of whole numbers. That is actually just add 0 to the set of natural numbers, you will get that. So it actually, this pattern continues. Okay. So we'll take a couple of examples, right? One, write the set which is given in a set builder form. For example, I have been given like x, where x square is less than 20 and x is a natural number, right? Suppose I have been given the set builder form and I want to convert it into a roster form, right? Roster form. So how do you do that is, the properties of the element is such that the square of that number is less than 20. X is a natural number and the square of that number is less than 20. So definitely you can say that so x is a natural number, so it starts from 1, right? So 1 square less than 20, yes, so 1 I will list. 2 square less than 20, yes, 2, so I will say 2, right? And then what about 3 square less than 20, yes, 3. And what about 4 square 16 less than 20, yes. But if I say 5, then 5 square is not less than 20, so I will stop here, right? So it means 1 2 3 4 is the roster form for this set builder form, right? Okay. So the next one is I would say is, right, is this is equal to, right? Yes, it is equal, right? Equal because, right? Because the repetition of the elements inside a set do not matter. So here if we see, right, A is repeated here, right? So in the second form we have written it only once, right? And the rest of the letters also we have written it uniquely here. So it means here the elements are repeated in the first case, whereas in the second case the elements are collected uniquely. So it means they are equal. Because why? Because repetitions do not alter the set, right? So that is the reason, alter the set. Okay, so that is the reason for that. So now let's take one more example. Convert, right? convert this to set builder form, right? So the first form given is the actually the roster form, right? So we have listed all the elements in the set. Now we'll have to inspect each of these elements and see what is the common property of each of these elements, right? In order to convert this to a set builder form, it is very important to understand the characteristic or the property of each of these elements. Is there any pattern between these elements, right? So we can see that in each of these elements, right, numerator is 1 less than the denominator, or the I can say denominator is 1 more than the numerator. So it is basically, when I say set builder form, I can easily form this as, right, some number p over q, right, p over q, where p, right, and q, they belong to what? Natural numbers, right? P and q belongs to the natural number set, and q is equal to p plus 1. And one more thing is and so here our elements are only 1, 2, 3, 4, right? And the numerator starts at 1 and numerator ends at 4. It means my p, right, is basically 1 to 4, right? So 1 is less than or equal to p less than or equal to 4. Similarly, if we see 2 to 5, right, q varies from 2 to 5. So it means that 2 is less than or equal to q less than or equal to 5. So this is the set builder form of this particular roster form that is given, right? So this is how actually we can convert from one form to the another form, right? So next we will talk about finite and infinite sets, right? Finite and infinite sets, right? So first let's define finite set, right? So finite means, before even that, actually let's first try to understand the sets, some common sets that we use. For example, let's first study, before finite and this one, let's understand what do we mean by empty set, right? What do we mean by empty set? So empty set is basically a set containing no elements. Containing no elements. So how do we represent that? Is either you use empty curly braces, open and close curly braces, or we use another symbol, this phi, right? We use this phi to represent the empty set. Okay, so it doesn't contain any elements, right? So it means number of elements in this set is 0, right? That's how we say that. Okay, say for example, if I have given a set builder form, which says a number x such that, right, x is natural number, x is natural number, and right, x is natural number and root of x square plus 2 equal to 0, right? So here what we have been given here is x is a natural number and it also is the root of this. Now we can see that x square plus 2 equal to 0, we don't have any real roots, right? So we know that x square plus 2 equal to 0 does not have a real roots. So it means that no natural number roots, right? But we have been told that it is a natural number. So obviously whatever the set builder form we have been given, there are no elements here. So no elements in this set. So hence we say this is equal to null set. So this is basically a null set. Correct? This is how we define that. Next we will actually understand finite and infinite sets. Okay. So what do you mean by finite set is, right? Let's look at finite set. A set which is empty or consists definite number of elements, right? Set which is either empty, it means no elements, right? It means no elements. A set containing no elements or empty or containing definite number of elements. Is called as finite set. Okay. Say for example, empty set is a finite set, no doubt, because it contains no elements, right? We know exactly how many elements it contains. And we looked at, say, the first example is empty set, right? Which is a finite set, right? Second one, we saw earlier prime factors of 20, right? Prime factors of 20. That was actually 2, 5, right? So this is also contains definite. We know how many elements are there, right? So it means it is also a finite set. Now if I say odd natural numbers. Odd natural numbers means 1, 3, 5, like that. So here, do we know how many elements are there? No, we don't know actually, because we don't know what is the maximum number here. So the number of elements is indefinite. In fact, we call this as actually infinite. There are infinitely many elements are there, right? Infinite. And that's why we say this is not a finite set, right? So similarly, natural numbers, they also like 1, 2, 3, it goes infinitely, natural numbers. And what about the rational numbers? Rational numbers are also like that. And what about integers? Integers are also like that. So similarly, you would say integers, rational numbers, irrational numbers, real numbers, all these are actually not finite sets, because they contain infinitely many elements. Okay, so that is exactly we come to the point of infinite set, right? Infinite set means a set which is not finite. It's very simple to define. A set which is not finite is infinite. Once we know what is the meaning of finite set, then infinite is nothing but a set which is not finite, means which which is not an empty set, and it is containing indefinite number of elements or infinite number of elements, right? So this is another concept that we need to keep in mind. Next comes cardinality of the set. Cardinality of set. So cardinality of a set is number of elements, right? Number of elements or objects, right, in the set. So definitely cardinality of a finite set is finite, right? It is some known number, right? So cardinality of a finite set is always a known number, whereas cardinality of infinite set is infinity. We don't know what is the size of that set, right? So that is the cardinality. So cardinality of empty set is 0. Number of elements in the empty set is 0. Okay. Okay. So next we will talk about equality of sets, right? Equality of set. So how do we define that is, if two sets A and B are such that for each element belonging to A, A also belongs to B, and for each B belong to B, capital B set, B small b also belong to A. So this is the mathematical definition. What does it mean is, if A and B have to be equal, right, then each of the element in A has to be present in B, and vice versa. Each of the element in B has to be present in A. That's what this means. The first condition says, for every element in A, right, that has to belong to B as well, B, and also for every element in B, it has to belong to A. This is the definition. If this is the case, right, then we say A is equal to B. Two sets we say are equal. Okay, so this is the equality test. Okay. So this is the concept that we have studied till now, and then we'll talk about the subsets, right? The next concept is subsets. Subsets. What do we mean by subset is, the definition is, right, let A and B be two sets. If A is there in capital A, means if small a is an element of the set capital A, and it also belongs to B. If A in capital A means, we say this symbol, right? So this is actually called as implies. If small a means if an element in the first set means that element is also there in the second set, right? So we say that small a belongs to the first set implies small a is also in B. If this condition is satisfied, then we say A is subset of B. symbolically we represent this as A, right? So this is the symbolic representation for the subset, right? For example, let us take A is equal to, right? A is equal to 1, 2, B is equal to, right, 2, 1, 4. So here we can see that each of these element of A, right, A, say 1 is present in B and 2 present in the A and is also present in B, right? So it means that, you know, this condition is satisfied. Small a belonging to the first set implies small a is also a member of the second set. So this satisfies what? So this means for each element of A, you know, it also is in B, right? Therefore A is a subset of B. Now here we have another terminology called as proper subset. Proper subset. What is proper subset is A is a subset of B and A is not equal to B. In this case we say, you know, in this case A is proper subset of B. So in the example here, right, A and B, A is a subset of B, we know that, because for each element of each element of A is also element of B, but A is not equal to B. In this case, right, here A is, right, a proper subset of B. Proper subset. We say it's a subset, and also specifically it is a proper subset. We say we have to note that, right, null set, right, null set is a subset of all the sets. You take any set, right? So phi is subset of any set A, capital A, right? So this is first important property. Second important property is, right, if A is not null set already, then, right, phi is proper subset of A if A is not equal to null. If A is not already null, then null set is proper subset of any non-null set. Okay, any set is subset of itself, right? Any set is subset of itself, because you can see that it satisfies this property, right? All the elements of that set are present in that set only. It means that set is subset of that set itself, right? So it means any set is subset of itself. So how we represent that is A is a subset of A for any A, for any set. In fact, you can say capital B subset of capital B. It doesn't matter what notation you use. Any set is subset of itself, including null set, right? This is including null set. It means phi is subset of phi, right? So this is what we need to keep that in mind, some common properties. So now we can see that earlier we talked about these natural number set, rational numbers, integers, irrational numbers and real numbers, right, and whole numbers. So we can easily now relate with respect to the subset, right? So we can easily see that the whole number set, right, is a subset of the natural number, right? Sorry, it is the other way around. Okay, natural number, right, set is subset of whole number, because whole number contains what? Whole number contains 0 in addition to the natural numbers. So natural number is a subset of the whole numbers, and then it is a subset of the integers, because integers contain negative numbers also, right? So it is so W is a subset of the integers. Now integers are subset of Q, correct? Integers are subset of Q. What is Q? Rational numbers. So integers are subset of rational numbers, and then rational numbers are subset of real numbers, right? So this is the relation we need to mix. N is a subset of W, W is a subset of Z, Z is a subset of Q, and Q is a subset of R. And we can see that N is a subset of even Z, Q, R. Whatever the right side terms, right side set comes, right, it is always a bigger set, right? So W is a subset of Q and R also, apart from Z, Z. Similarly, Z is subset of R as well, right? And the irrational number is a subset of real numbers, right? Next we will talk about intervals. So in mathematics, we come across, while studying the numbers and dealing with the numbers, right, we come across different intervals, right? So intervals of numbers as sets, right? So first let's consider the open interval, right? Open interval. So how do we represent the open interval? Is we use this parenthesis, right? The left parenthesis and right parenthesis, and we say the A comma B. So what does it mean is, so this is A is called as a lower bound, right? So this is A is called as a lower bound, which is not included in this, and B is upper bound. This is the A is the smallest number, which is not included here, and B is the biggest number, which is not included in this. So these are basically not including, we say, because this is the open interval. When we say open interval, it means both lower and upper bounds are not included. Say for example, I would say my set is an open interval, right? It is a assume that it is a real number set which is from say 1 to 3, right? It is an open interval. How do we represent that on the number line is, right, you have 0 here, you have 1 here, right? For example, you have 2 here and you have 3. So 1 is this, it is not included, right? When it is not included, the lower bound, we put that as a small circle, and 3 is also not included, right? So this we put a circle around that. So whatever is in between, right, this all the real numbers, right, which fall between 1 and 3, this is the intent. This is my set actually. So all real numbers between 1 and 3, but not including, we would say, because this is an open interval. So in the open interval, the lower and upper bounds are not included. Now we can understand the closed interval, right? What is closed interval? So closed interval is where, you know, both the lower and upper bounds are included, right? So it means I would say A comma B, both are included. For example, if I say real numbers between -1 and +1, right? Real numbers between -1 and +1. So we use the square bracket here for the closed interval, right? And how do we represent that on the number line is, this is 0, this is -1, this is +1, right? Now here we put a dot here, right? The filled circle, small circle, filled small circle. Filled means actually these two are included, right? That is what we mean by closed interval. It means that both the upper bound and the lower bound are included. So here all the real numbers between -1 and +1 are included in this set actually. Okay. So the next one is third one is half open, right? So the next one is half open. So here in the case of half open, right? So one of the lower and upper bounds are open and another one is closed one, right? So that's how it will be. So in the half open means, you know, one of the bounds is not included, right? So it means, you know, it could be the lower bound which is not included. In that case, you know, we say not included the lower bound, but the upper bound is included, right? So the another form is the lower bound is not included, lower bound is included but upper bound is not included, right? So here A is not included, whereas in the second case B, the upper bound is not included, right? Not included. So this basically is a half open intervals, and open and closed anyway we already have discussed. So next we will discuss about the power set. Okay, power set. Okay. So power set is defined as set of subsets of a given set is called power set. Power set. For example, suppose A is given as right 1, 2, right? Now what we have to find is all the subsets of the A we have to find out, right? First find all the subsets, find all subsets of A. All subsets of A means we know that null set is part of null set is subset of any set, right? So the first set that comes to mind when we talk about subset is the null set, which is a special case or which is a special set which is subset of all the sets. So 5 is the first one. Next one is all the one elements, right? Say one is a element, right? So you collect that and form a set. That will also be a subset of A, right? So it means 1 is a subset of A, and then you take element 2 and that is a subset of A, and now we know that, right, that set is subset of itself, right? So it means 1 comma 2. So null set and this set are subsets of any given set. So when we think of subsets of a set, the null set and that set itself will be the default subsets, right? So in this case we can see that phi and that set itself are already part of the subsets, and these another combinations of come into picture. So how do we find is a subset of any given set is, first you list out the null set and that set itself, right? Those already come as a default subsets, and then you start combining, right, each of these elements. First take one at a time, one element at a time you list out, right, and then 2 at a time you list out, till we get the number of elements which are present in A, till we exhaust all the number of elements in the A, right? So this is how we found. So therefore the answer is power set of A is equal to, we again, you see, this is actually set of sets, correct? So this is a set containing inside the set we have another sets, right? So those sets are elements of this set. So phi is there, 1 is there, 2 is there, and then 1 comma 2. So this is the power set of the given set, right? So another one, if you want to take, is a second example is, say if I have A is equal to PQR, right? I can directly say phi anyway will come as a first subset. Second is single elements, collect all the single elements P, Q, R, then collect 2 elements at a time. So PQ, you take PQ, but here order does not matter, right? Just take the collection of them, right? No need to order, right? Because in the set we don't, P comma Q is same as Q comma P in terms of set, right? Because in the sets we don't really care about the ordering of the elements, right? So 2 element sets you collect, that will be QR, and then you have RP, right? And then 3 element set we have PQR. So we can see that, right, when the number of elements, right, in the first case P of A is this, right? So number of elements, right? So the number of elements in the set, power set of A is 4. In the second case, number of elements in the power set of A is what? Actually, if you see 1, 2, 3, 4, 5, 6, 7, 8, right? And we can see there is a relationship between the power set, number of elements in the power set, and the cardinality of A, right? So here in the first case, what is the cardinality of A? N of A is 2, right? So what is the N of P of A is 4. That is actually, we would say 2 to the power of N of A. So this is the generic form. This holds here also. So here we can see in the second case we have 3 elements, right? The cardinality or the number of elements in A is 3, and number of elements in the power set of the A, right, that is equal to 8. So we have a relation between N of A and N of P of A. What is that actually? N of P of A is equal to 2 to the power of N of A. So this is the general formula. The number of elements in a power set, right, is equal to 2 to the power of number of elements in that set. in the given set, right? So this is the power set. So next we will talk about Venn diagrams, right? Venn diagrams. So here in the Venn diagram, right, we will represent the sets as circles, right? Suppose A, B are sets. We represent them as circles, and suppose if there are common elements between A and B, we actually represent that as a intersecting circles, right? So in general we can assume that this might be present or not. In general, we represent something like this. So the A and B are actually represented individually as circles, or sometimes we can represent that as ovals, as a oval, but it is okay, like either form is okay, either oval or circle is fine. And then we represent as a rectangle to represent a bigger set under consideration. So this we call this as a universal set U. So U is basically a bigger set containing all the sets under consideration for a given problem, all sets under consideration. For a given problem or a situation or a circumstance, this U represents the combination of all the sets involved, right? So it means it contains all the elements present in all the sets under consideration. So this is called as a universal set. Universal set, right? Universal set. So we can easily see that A is a subset of universal set and B is a subset of universal set, correct? Yeah, because since U is a bigger set which contains these two sets, so individually these are basically subset of the universal set. Okay, so this is the representation of the Venn diagram. If we have say another C as another set, for example, I will represent that something like this. So if I have a C, set C, then C is also a subset of a universal set, right? Okay. So now we will understand the operations on the set, right? Operation on the sets. Okay. Let's first take union of sets. Union of sets, right? Suppose for simplicity, let's take two sets, right? A and B, right? Say A equal to 1, 3, B equal to, right, 3, 8, 9. So A union is represented like U here, right? A union B is basically you collect all the elements present in A and B without repetition and just put it here. It means it is 1, 3, 8, 9, right? So how do we define A union B mathematically? So this is the way we get this A union B is collect all the elements without repetition in the given sets, right? So this is the procedure we do. Now what is the actual definition in the set builder form is A union B, right, is defined as, right, an element, right, an element A, for example, small a, where A is belonging to the first set A, right, or A is belonging to the second set. So this A union B is such that the element in the union set is either present in A or present in B or both actually, right? So that is the union here we are talking about. So this is the precise definition of the union of sets, and example we have already taken here, right? Next, we will try to understand from the Venn diagram, right? From the Venn diagram we will try to understand. Suppose the same thing, right? 1, 3 and B is 3, 8, 9. Let's draw a Venn diagram for this, right? Right. A and then B, right? A, B. In the A we have 1, 3 is common, right? So I will put it inside this area here, which is intersection of A and B, whatever area is there, right? This area actually I will put it as a 3 because 3 is belonging to both A and B, right? That's why I have put it in this section here, pictorially. And then 8 and 9 are here, right? We can clearly see that A contains 1 and 3 and B contains 3, 8, 9, right? And this is the universal set under consideration. This is how we represent the union. And what is the union here? This whole area, right? I am just marking it with the slashed lines, right? This whole area, slashed lines, they are actually represent the union set A union B. Okay. Next is intersection of sets, right? Intersection. Intersection. So in the same example, right, A and B here, A intersection B, how we find is collect all the elements common between the sets. So that is nothing but, in this case it is 3, right? 3 is the common element. Common elements between the sets, right? That is called as intersection of the given sets. In fact, we can extend this to the multiple sets also, right? Not only 2, you can extend it to 3, 4, 5 like that, right? The same case here for the union also, you can extend it to the multiple sets also, like 3 or more sets. So here the precise definition of A intersection B is, right, it is an element, for example X, where X is belonging to both A and B. That's why I will say and X is, so this element is such that the element of an intersection is such that that element is belonging to both A and B, right? So that's why we symbolically we represent that as X belonging to A and X belonging to B is nothing but the A intersection B. And in the Venn diagram case, right, this is A, this is B, this is 1, 3 is the common, 8, 9, right? This, whatever is the dashed lines I have given, right? This is basically intersection. So this area, whatever I have marked with the dashed lines, this is nothing but the intersection, right? That is A intersection. So we can extend it to 3 or more sets. So we have to collect common elements of all the given sets, right? That is a general definition of intersection. Okay. Next, we'll talk about some properties of the intersection, right? Before that, actually, let's understand the properties of both union and intersection, right? Properties of union of sets. Properties. We need to note these properties of union operation. Properties of union operation. So the first one is the commutative law, right? Commutative law. Commutative means A union B is equal to B union A. The second one is, right, the associative law. Associative law. What is associative is if we have 3 sets A, B, C, and we are doing the union of the first 2 and then union with the third one, it is same as doing the union of the first with the union of the second and third. So here the grouping does not matter. For the union, you can group the first 2 and do the union before calculating the union of the entire operation, or you can actually do the union of the second and third elements before doing the union of the entire operation, right? The third one property is law of identity element, right? Law of identity. So under the union operation, right, the null set is considered as an identity element. That's why you take any set, you make make an operation of union with the null set, you get the same set. It is same as null set union with that set. So when you make an operation of union with union with the null set, you will get back the same set, right? So that is the law of identity element. So we say that phi, the null set, right, null set is identity element under union operation, right? Union operation. The next one is idempotent law, right? Idempotent law. Idempotent law. Idempotent law says it is you take any set, union with that set itself will produce the same set, right? A union A is same as A. And the last one is the law of universal set law, right? So you take universal set and you union with any set inside it, you will always get the universal set, right? So that's why now to distinguish, right, you use the capital U, right? Capital U for the universal set, right? Capital U. Because any set is a subset of the universal set. That is what is the reasoning for this universal set law. Okay, and next we will understand the properties of intersection operation. Right, the properties of intersection, it holds same as the first one is a commutative, right? So this commutative, it holds same, right? The first one is again commutative law, means A intersection B is same as B intersection, right? The second one is, right, the associative A intersection B first you do, and then intersection with C is same as A intersection B intersection C. Okay, the third one is idempotent law, right? The law of, okay, let's talk about the law of the null set and the universal set. Law of null set and universal set. What it says is, you take any set intersection with the null set, right? Null set intersection with any set is same as any set intersection with the null set is always null set. And then you take any set and you union with you intersect with the universal set intersect with any set is same as any set intersection with the universal set. You always get that same set A, right? So this is the set law of the null set and the universal set. Okay, and next the fourth one is idempotent law, right? Idempotent law. Okay, what it says is A intersection A is A itself, right? And then we have a distribution law. So here are the distribution laws. So distribution law. So what it says is the intersection distributes over right? Distributes over union, right? What does it mean? A intersection B union C. A intersection B union C is equal to A intersection B union A intersection C. So we can see that, right, the intersection is distributed over the union. Okay, and then let's talk about the difference sets, right? Next operation is difference operation. Difference set. Difference of sets, right? Difference of sets. Suppose A and B are sets. We define A minus B as, right, an element X which is there in A but not in B. We say X is in A, right, and X is not in B. That is the definition of the A minus B. Whereas B minus A, right, if you see, its definition will be different because X here is belonging to B and X is not in A. Therefore we say A minus B here is not equal to B minus A. There is no distribution. So no commutative law, right? Commutative law is not satisfied here for the difference of sets, right? So that is very important to understand. For example, difference of sets. So suppose A is equal to, right, 1 2, B is equal to, right, 2 3 9. A minus B, collect all the elements of A which are not in B, right? So how do you do that is 1, you start with 1 is there, no, so you write it. 1 is there in B, no, so you write it. 2 is there in B, yes, so don't count that. So it means A minus B is only this B. Now find out what is B minus A. In the B minus A, what we have to do is collect all the elements of B which are not there in A. It means now start with the first element of B. 2 is there in A, yes, don't count that. 3 is there in A, no, so you collect that. And 9 is there in A, no, so you collect that. So 3, 9 is B. So clearly we can see that A minus B is not equal to B minus A. This property is satisfied here. Okay. Next we will talk about complement of a set, right? Complement of a set. If A is a set, if A is a set, and U is universal set, then complement of A, right, complement of A is defined as, right, an element small x, for example, where, right, x is not in A and x is in U. X is part of the universal set. What does it mean is complement of a set is the set of elements which are not in A but which are present in the universal set. It means you collect all the elements which are not in A, that's all, right? Say for example, let's take, say, universal set U as 1 3 9, and let's take A as 2, we cannot take 2 here, let's add 2 here, 1 2 and 9, right, for example. What is A? Complement of A we represent like this, right? A dash is collect all the elements in the universal set which are not in A, right? It's basically, it is this definition is same as saying U minus A, right? All the elements in the universal set which are not in A is nothing but the complement of A, correct? This is another definition. U minus A is another definition for A. So I say A complement is U minus A, right? So this is how we actually figure out what is the complement of A. So here A dash is collect all the elements in the universal set which are not in A, means 2 is there in universal set, yes, you forget about that. 9 is there in the universal, forget about that. So rest of the elements is you collect 1 3. This is the complement of A. Okay. Okay, properties. Next let's look at the properties of before even going to the properties, let's look at from the Venn diagram, right? Let's look at from the Venn diagram perspective. So in the Venn diagram, right, suppose if we have this as a universal set and A and B are here, right? Say for example A and B are there, right? And then suppose I want to find out what is A complement is, right? All that is not A, right? You mark everything, right? You mark everything except A, right? This is A, right? This is A. So you mark all the area in the universal set which is not A. So except A, rest all in the universal set is A complement, right? So I would say this shaded area represents A complement, right? Similarly B complement. So B complement, I will write it as a the backward slash, right? So how do I do that? Backward slash, right? You mark everything, right, except B, right? Except B, you mark everything. So this means this area is there, right? This area represents B dash. Okay. Now let's look at the properties of complement sets, right? Properties of complement of set. So the first one is A union A complement is always universal set, right? It is same as A complement union A, right? Because union is commutative, right? So either you do A with A complement or A complement with A, you will get the same answer as the universal set. So the next one is A intersection A dash. A dash is a complement of it. So A and A complement are complementary, right? It means there are no common elements here, so it has to be a null set. It is same as A complement intersection. Okay. So the next one is we call this as a De Morgan's law. De Morgan's law. De Morgan's law is A union B dash complement of A union B, right? Complement of A union B is intersection of complements of the sets, right? So it means, I would say it is A complement intersection B complement. Okay. Similarly, A intersection B complement, right, is A complement union of B complement, right? A complement union B complement. And then we have double complementation, right? So double complement of complement, right? Double complement law. What it says is complement of a complement is that set itself, original set. Complement of complement is the original set itself, right? Then the last one is law of null set and universal set, right? What it says is the null set, the complement of a null set is a universal set. Complement of null set is universal set, right? And complement of universal set, right, is null set. Okay, so this completes the theoretical aspect of the sets for the 11th standard. So next, in the next discussion, we'll solve some examples, exercise problems, so that we can apply these concepts in solving the problems related to the sets. Okay.